Good call. So again, this extra OH from the conjugate base forming from up here, we get this extra OH, which brings our pH, instead of being at 7 at the equivalence point, we're at 8.73. Now, an interesting thing, this will come into play next week, is the fact that that's why we use phenolphthalein when titrating a weak acid with a strong base. That's why we used phenolphthalein last time, because it actually changes between 8 and 9 pH. So if you were actually doing a strong acid, strong base, you wouldn't want to use phenolphthalein because you would actually have then more base added to get that color change. You would want something that changes right around 7. Now, going to that point, those indicators change right at their the pH equal to their pKa. Because if we look at the Henderson-Hasselbalch equation, that's when the A negative and the HA are equal, because that would be 1 over 1. What's the log of 1? 0. So pKa plus 0 equals pH. That's what you're looking for in the indicator. You want the actual change in the pH to occur right at the pKa of that indicator, because that's when we start switching from, concentrations, changing. What does that mean? I'm going with the lab tomorrow. If this is the equivalence point right here at 23.58, at what point do we have the weak acid and its conjugate base at equal concentration? Below that. I will accept that answer. Looks. Go ahead, Piper, or whoever. If this is when all of the weak acid is gone, where's the point that we would have half weak acid and half conjugate base? This is where we have only the weak acid. As we add the NaOH, the weak acid becomes neutralized, right? So where's the point that we have half and half, or I should say 1-to-1 ratio of it? Because here it would be 1-to-0, and here it would be 0-to-1. So where would it be 1-to-1? In the middle, right? In the middle. So what's the middle of 23.58? What 11.5 something? So right about here, right? That's where the ratio equals each other. So what I'm saying is we have the A negative equal to the HA, right? And if these are equal, this concentration over this concentration will equal 1. And we know Henderson-Hasselbalch is pH equals pKa plus the log of A negative HA. So if this is 1, then log of 1 is 0. pKa equals pH. Right? So at the middle point of this right here, if we find the pH, that will equal to pKa. Yes? What does that mean? Well, we can take 10 to the negative that pH, and we can get the Ka. And that's the idea of the laboratory tomorrow, right? We're actually going to try to do a little bit better because of well, I mean, let's face it, we haven't been in the laboratory as much as we wanted this year, so our lab technique is not the best. So what we want to do is we want to cut some more points in here. At this point, we would have 3/4 the acid to 1/4 the conjugate base. And at this point, we'd have 3/4 the conjugate base to 1/4 the acid, right? So then we can put, instead of 1 to 1 in here, we could put for this one down at the bottom 3/4 and 1/4. And then for this one at the top, we could put 3/4 divided by 1/4 and then take the log of that. We don't even need to know the concentration or anything. We can actually use the fraction because that's what it should be at these points. Questions there? So basically for tomorrow's lab, you need a nice graph. Like again, don't just stop at the point of equivalence. Keep going so that we can see this curve up here in the plateau. The problem with all of this is the point of equivalence, because at this point we don't have any of the acid left, the HA. So we can't actually use this, right? We will know the pH. So we'll have the OH negative, OH plus positive from that calculation. And we can use an ice table to determine the concentration of this and that, and then we can use this formula. Ka equals and remember, both of these formulas are related, right? We've shown a few times poorly, unfortunately, how to convert this to this by taking the negative log of everything. But we know that they are basically the same. You can change them using math, right? All right, then. Let's take a look at this last one then. It says calculate the pH of calculate the pH of the 25 milliliter sample of 0.100 molar acetic acid following the addition of 30 milliliters of 0.106 molar sodium hydroxide. So again, we have our formula HC2H3O2 plus NaOH yields H2O and C2H3O2 negative. Now the amount of the starting acid is not changed. So again, we still have that 0.0025 moles. Again, we have a reaction taking place here. This is reacting with this to form H2O. And this is the one we need to figure out. We have 30 milliliters. So I'm going to change that to 0.030 liters. Every 1 liter is 0.106 moles. That'll give me the moles of that. Oh no. I'm in some weird mode. Quick. 0.03 times 0.106. We get 0.00318. Remember, this is a reaction, so we have a limiting reagent. So which one is the limiting reagent? The acetic acid or the sodium hydroxide? Acetic acid. That sounds loud. Quiet down up there. All right. So we're going to end up with 0 of this. We're going to end up with plus 0.0025 of this. So 0.00318 minus 0.0025. That gives us 6.8 times 10 to the negative 4th. That's what's left. So what does that mean? That's how much what's in there. So this is a strong base. That means it's the concentration of
OH.
OH, or sodium hydroxide. Yep. I'm sorry, it is not the concentration, it's the number of moles. And this is the concentration of the weak base, which is the same concentration it is up here, right? Right? That's the moles. Yeah, I'm sorry. Same. This is the number of moles of the weak base, which is the same as it is up here. Now the difference is that instead of dealing with 48.58 liters, we're dealing with what? Yeah, right. 0.055. So let's take that 6.08 divided by 0.055. That will give us 0.123, actually 0.124 moles per liter of hydroxide. Remember, we're trying to calculate the pH here. So we also have this in 0.055 liters. A 0.045. One thing we can do is this, is let's take 6.8 times 10 to the negative fourth plus 0.0025. That's the total moles that we have divided by 0.055. You can see that that is not going to change our thing here. This right here, let me make sure, one time, 0.00318 divided by our minus 0.0. Height. Insert. Yeah. So this 0.124 molar OH negative, that's going to be the primary of our OH negative. Because if we sit here and take this, we get, let's do it. Well, we get this. Whenever we multiply this through, we get 5.35 times 10 to the negative sixth molar hydroxide. Now, how does this compare to this moles per liter of hydroxide? If we add these together, is it going to change this? I probably missed one. Let me check. Divided by 0.055. There's your check. 0.0123 or 124. Thank you. Because I would have hated that later, right? But if we add this to this, is it going to change it at all? 5.35 times 10 to the negative 6? No, right? Remember, that's what we got whenever we took this up here. And we recalculated the moles. Now I realized that this is in 0.04858 liters. We could change that to this 0.0025 divided by 0.055. So instead of this right here, we get this. Well, let's go ahead and do it. Let's take the KB, which is 5.56 times 10 to the negative 10. 5.56 times 10 to the negative 10. That's the KB. And I'm going to do this in my head, but I can write it down if you want. Remember that the amount of hydroxide in this case is equal to the square root of the KB times the concentration of the OH minus. In this case, it is this 0.0025 divided by 0.0055 from here, right? That's our conjugate base. That's the molarity of the conjugate base. We're going to multiply that by the Kb. And then we will take the square root of that. Again, from this formula right here. I should put, this is the, let's put MB there for the molarity of the base, the conjugate base in this case. So the hydroxide for a weak base is equal to the base constant times the molarity of the base. So that gives us 5.02 or 5.03 times 10 to the negative 6. If we try to add that to, this looks like garbage now. What was it? 0.0 what? 0124. So if we add this times 10 to the negative 6 to 0.0124, will it change it? No, right? It's a very negligible change. So the fact that sodium hydroxide is a strong base, once we go past that equivalence point, and then we have excess sodium hydroxide, who takes over for figuring out our pH? The leftover sodium hydroxide, right? The weak base that was formed, it has a low Kb, so it's not going to have that big of an effect. So then you could do all this, or you could take that to heart and sit there and say that that's most likely what's going to happen. Totally up to you. But what we end up seeing is that this is the major contribution of our hydroxide ions. So how do we go from pH from there? I'll accept that. Negative log 0.0124. That right there is our pOH. And then we take 14 minus that. And that right there is our P. Acidic or basic? Well, we are well into the basic range now. Take a look there. We're probably getting ready to plateau here. That is the 12.09. That's after our equivalence point has been reached, and we added more base than we needed. So that's where we at. Questions there? No. All right. Please download this laboratory, and let's talk about this today. I do want to show you guys. I went ahead and I wasn't liking the results I was getting from PhD last time, so I went ahead and looked up LabPlus Pros. If you've taken physics, you can I believe. No, all right. What's that? Okay. All right. So LabPlus Pro is basically like you have these different things that you can hook into these little handheld devices. So we're using those instead of the little stick. You remember the things that like little stick, looks like a thermometer, but it's not. So the idea tomorrow is that those that come in will do a titration. This doesn't look as good as it could, in my opinion. Better. All right. Excuse me. So we want you to determine the Ka for a known monoprotic acid from its pH value. And then in the laboratory, we want you to determine for an unknown monoprotic weak acid. So we've got 3 different powdered acids back there. We know that weak acids, protonates, they ionize, they don't ionize completely. They ionize based off of what we call an equilibrium constant. That equilibrium constant for acids is called the Ka. Again, just like every equilibrium constant, it is products over reactants, where the product here, one of the major products that you're concerned about, is the proton concentration or the hydrogen ion concentration, whatever you want to call it. If we know the original concentration, and we can determine the hydrogen ion concentration, then the Ka can be determined, because the hydrogen ion concentration is going to be equal to the conjugate base concentration, right? That's why we can always do that x squared thing up there. A pH meter, we're using the things, but they work the same as the principle of voltage difference between the inside of the probe and the solution. If you look at the bottom of those, maybe you did last time, you see like this little bulb. That's what they're talking about there. Acid equilibrium constant for the reaction is the Ka. It provides a quantitative measurement of the degree to which the acid dissociates. So if Ka is small, it means that the acid does not dissociate. It does not give up that hydrogen ion easily. If it's big, it indicates that the acid dissociates quite well. Now keep in mind our strong acids, HCl, HBr, HI, and then the 8s like sulfuric, nitric, and perchloric. When a weak acid is labeled, for example, 0.100, this refers to the initial molarity, right? That's the initial molarity. The amount that it's dissociated can be determined by the measuring the pH of the solution. And basically, we're going to measure that pH over and over and over again every 1 milliliter until we get to where we see a big change. And then we're going to measure it every 0.5 milliliters. That way we can get a graph that looks like this. All right. So here is the procedure for that. You are going to obtain, and this isn't the same one I had yesterday. Let's have more information on it. Let me see if I can go grab it. I think it's in my room over here. So those of you that are going to be here tomorrow and the others as well, make sure you do these pre-lab questions tonight. That way you get a little bit of an idea of what you're getting into. This is the first step of that. If you recall up here, it said, determine the Ka for a known monoprotic weak acid from its pH value. That's what they're giving you right here. They're giving you the pH of these. You're going to figure out, you're going to figure out the pH of these, and then you're going to figure out the percent of dissociation. Then tomorrow, here is the unknown monoprotic acid. We are using about 2 grams. Well, that's pretty important. Otherwise, you're going to go through all of the sodium hydroxide, and you just don't want to do that. You'll dissolve that in 100 milliliters of water. This is very big and important. It's important we do that so that we know the final concentration. We're going to assume no change in volume with that. So your in sample should be 100 milliliters of the acid. That way, when you're adding your sodium hydroxide, whatever you get for your base at your equilibrium point, your equivalence point, right? Whenever it's totally titrated, the end point, if you will, whatever the volume of that base is there, will be added to that 100 milliliters to give you your final volume. And what does that mean? So that's what we're talking about whenever we talk about this 0.055 liters. That's the final volume at each of these points. So at the equivalence point here, the final volume was that 48.58 liters. So to find that, you will sit there and take the volume of the base at the equivalence and add it to this 100 milliliters to give you your final volume of that. That will allow you to find those concentrations. Titrate it, the pH will change very rapidly. So again, notice that 0.5 milliliter increments around the equivalence point. After you see the pH going boom, 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 make sure you slow down your roll on that and add only 0.5 each time. Now, obviously, it doesn't need to be exactly 0.5, but those are just estimates. Now, here's the thing. You need to take point of your equivalence, but then you also want to make sure that you reach a pH of about 12. That's when you'll stop, or whenever you run out of base. That's what's going to give us, and unfortunately, this is not the full graph because the print was garbage, but that's what's going to give us that rounding off point of that graph. Again, looking at that graph, we can cut that into half and then into quarters. And if you're doing the lab tomorrow, if you're helping the calculations with the lab, that's what you want to read this paragraph over and over again. You're going to create points A, B, and C, and D is going to be your equivalent point. So A, B, and C, A will represent 1/4 being just neutralized, 1/4 being the conjugate base, and 3/4 being the leftover acid. The concentration at point A will be 3/4 acid and 1/4 conjugate base. At B, that will be your 50-50 mark. So the conjugate base and the acid will have equal concentrations. And then C, you will have 3/4 conjugate base and 1/4 of your weak acid that you started with. Now, why do you need that? Well, because of your Henderson-Hasselbalch equation. You will basically put for A, 1/4 over 3/4. For B, 1/1. For C, 3/4 over 1/4. And then D, you can't really use this. You got to use an ice table. But that's the idea. For point D, it should be based on the pH at the equivalence point. That is basically this right here. That's this problem right here for that weak acid. And basically you will find, since you have no more moles of the acid or base, you'll have to do the salt hydrolysis, which is that ice table, to go back and say, okay, how much of this changed? This is that salt hydrolysis where you have this reacting with the water, then hydrolysis, right, to produce the base and the weak acid again. Since you have no more of the NaOH and you have no more of the weak acid, the salt hydrolysis takes place. And then you basically go through and fill out this. Right. And you're going to basically get an average of several of these points for the Ka. Since you are using the Henderson-Hasselbalch, you'll be able to basically solve for that pKa and then take that to the negative power and get the Ka. Then you average those Kas together with the Ka that you get from the salt hydrolysis, and basically use that Ka then to determine which one you have. Again, if you printed this out early, there's been a change. This sodium, we did not have any of that, so we had to change that to potassium. We didn't get a hold of that, and we didn't get a hold of that. So we only have 3. Luckily, I think we only have 3 or 4 people coming in tomorrow. Questions there? All right, let's take a look then at this new device. That way we don't come in with any surprises. Same old titration setup. Oh, am I frozen? I'm frozen. What's that? So we take a look, you know this setup, this guy right here, this is the burette setup. This is the only new thing. I don't even know how to show it. Dang it. Yeah. Basically, it looks like this. This is the probe. This is the hardest part of this whole thing. You unscrew this, and then you can pull the probe out. This needs to set like facing up because it has a solution in there that protects the probe. Let me grab these two solutions over here real quick. So, can you guys read that? What's it say? Good. So this is distilled water. We put that in there and you can see it goes up to 6.14, which makes sense because distilled water will absorb carbon dioxide from the air to make carbonic acid as it sits. And this sat open all night last night, so it's probably saturated, like saturation point for it. This is a buffered solution right here. The pH of that buffered solution is what probably? Probably 4, right? You can see that these are a little bit better than the ones before because the ones that those of you at home, Lily and you know those bounced around a lot and you were like, okay, let's just take it now. So these are a little bit better. Notice every time I'm rinsing it off with distilled water, you can also do that like this. And if you can't see that at home, basically I'm using the distilled water thing. The what's it called? Bottle. What do you think the pH of this solution is? What a glare. All right. It's actually supposed to be 10, but I'm assuming that also some carbonic acid formed in here overnight from the carbon dioxide. But we get 9.71. This is supposed to be a 10.0 buffer. But you can see that this works a lot better than, in my mind, there you go, up to 10. Works a lot better than the pH meters that we used before. So that's it. Basically, you turn these on. Now, keep in mind, they have to be stored in this. So you need to make sure that you put that back on and you tighten this up. When you tighten this up, it creates a seal around that. But it's not a perfect seal. So when you're all done with it, because we're using these next week as well, kind of make sure that you loop the cord around the sink in some way that makes it so it does not fall over, like so. Can you see it? Make sense? All righty then. That's what I got for today. Friday, we'll talk about the question that you guys did last night, 2002 thing. And then we'll also assign a buffer problem because next week we want to deal with a buffer lab. You guys are going to make buffers and then you're going to test the extent of them. Questions? All right, then. That's all I've got.